In this video, I want to talk about the significance of the haloform reaction, this new reaction in this chapter, and also the mechanism for how it works. And then we'll apply it in the context of synthesis in future videos. So first, the significance. What does the haloform reaction do? It takes a methyl ketone. So that's a ketone that has a methyl group on one side. So notice you have a ketone here, carbon double bonded to oxygen, with a carbon on each side. So this is a ketone. But one of the carbons on one side is a methyl group. That orange highlighted area is a methyl group. So this is called a methyl ketone. Now, in a sort of short-sighted view of things, you could say, well, the haloform reaction turns a methyl ketone into a carboxylic acid. That's technically true. That's exactly what it does. But take a second, sort of relax your eyes, zoom out. If you have a carboxylic acid, what that really means is that you turned the methyl group into a potential leaving group. So by turning a methyl ketone into a carboxylic acid, you open up all of the nucleophilic acyl substitution reactions. You could replace that methyl group with a longer carbon chain, right? You could use a Gilman reagent. You could turn this into thionyl chloride and then use a Gilman reagent. Or you could turn it into an amide. You could use thionyl chloride again and then treat it with excess ammonia or with some amine. And you could start to create proteins out of it. You could turn it into an ester. Any of the carboxylic acid derivatives are open to you. So in the short term, the haloform reaction turns a methyl ketone into a carboxylic acid. But by doing that, it opens up all of the nucleophilic acyl substitution reactions that you learned for carboxylic acids and their derivatives. The other significant thing about it is that, and so effectively now when you see a methyl ketone, you want to think, I can turn that into almost anything by first turning it into a carboxylic acid using the haloform reaction. The other reason why this is significant is because it changes the solubility of molecules. One of the most common things that your liver does to toxic molecules that you ingest is it turns them into carboxylic acids, because carboxylic acids have a lot of polar bonds, so they're really soluble in water, right? Like dissolves like. Polar solutes dissolve in polar solvents. Water is really polar. So think about all the ways your body tries to get rid of a toxin. You can puke it out, you can defecate it out, you can pee it out, you can get it out through mucus, right? You can vomit it out. All of those are solutions whose solvent is water. So all of those are solutions whose solvent is polar. And if you want to get something out of your body, you need to make it more polar, because then it will dissolve in those solutions better, and you'll eject more of it more efficiently. So by doing this haloform reaction, you can make things more water soluble. That's maybe another perspective that you can use to look at it from. Okay, so effectively you take a methyl ketone, turn it into a carboxylic acid, and now you've seen the significance of that, both from the perspective of solubility, this is now more soluble in water, and from the perspective of synthesis. You can now do any nucleophilic acyl substitution with that. Okay, well, how does it work? If you followed along through the early videos, the first maybe 4 videos in this chapter that I put up for this chapter, you'll see a trend as we go through all of these reactions. In the first step, you almost always have an acid or a base. And that's because that catalyzes the keto-enol tautomerization and makes the alpha position nucleophilic. That's what happens here. If you take this sort of alpha carbon, now notice we have 2 alpha carbons here, but remember the reactivity of the alpha carbon has to do with the acidity of the alpha hydrogens. This carbon on the left does not have any alpha hydrogens, and so it cannot turn into a nucleophile because nothing there is going to get ripped off here. But if you take that molecule and you treat it with sodium hydroxide, when you put that in solution, the positive sodium floats off in its own direction, the negative hydroxide is able to act as a base. That hydroxide can steal this alpha hydrogen and create the alpha carbon nucleophile there. So after you do that, you'd be left with this lone pair with a full negative charge on the alpha carbon. And you'd also have water in the solution. This would have turned into water. In other words, you have a carbon nucleophile. Well, what else is going to be present in the solution for it to attack? The bromine. It can attack a bromine and really sort of do an SN2 reaction. As the bromine isn't a perfectly nonpolar covalent bond, but as it floats close to this negative charge, the electrons in the bromine atom all run away from the negative charge. They're repelled by it, and the side of the bromine that's facing it becomes slightly positive. So you sort of induce a dipole there. You make the bromine an electrophile. The nucleophile attacks it, kicks the other bromine off as a leaving group. So really very similar to an SN2 reaction. And what you end up with is your same original molecule, just on the alpha position, you have a bromine. Okay, well, we've seen alpha bromination before, but here we have sodium hydroxide. What we've seen before was with an acid. And now you'll see the significance of why we used an acid before, because if you use a strong base, what happens is, if your alpha carbon is a methyl group, there are more hydrogens there for a base to steal. Now remember, one of the big important things here is that you have this methyl ketone. You have a methyl group on the side of the ketone. So if you have that methyl group, this base can steal another hydrogen. The electrons snap back onto that alpha carbon. So you again form a carbon nucleophile. And if there's still bromine in the solution, which there is, then a similar thing happens as before. When the molecule gets close to the negative charge, it induces a dipole. The electrons flee the negative charge. The side that's facing the negative charge becomes slightly positive, and this carbon nucleophile attacks the bromine, kicks the other bromine off, effectively an SN2 reaction. And now you have a second bromine on that alpha carbon. Well, that alpha carbon can't stop and won't stop. It is living its best life, getting rid of all these acidic hydrogens. So there's still another hydrogen there. If it's a methyl group, then it has 3 hydrogens on it. So if there's still more hydroxide in the solution, which there is, that hydroxide will act as a base and steal that last acidic hydrogen. And the electrons will go onto the carbon. So we have our carbon nucleophile again, and that can do another SN2 reaction with the bromines in the solution. So this can attack one of those bromines in which you have that induced dipole, kicks the other bromine off. This is our last sort of SN2 reaction we can do on that alpha carbon, and what we end up with is 3 bromines on that carbon. Okay. So I guess that makes sense, right? I mean, if it makes sense that this alpha hydrogen is acidic, and once it's a nucleophile, it can attack a bromine, well, then if that makes sense, it can make sense that that would happen 3 times if you have 3 hydrogens there, so that you replace all 3 of the hydrogens, in this case, with bromine. Okay, what then? Well, we still have more hydroxide in the solution. There are no more acidic alpha hydrogens left. So, what can this do? OH- is not just a strong base, it is also a strong nucleophile, and the carbonyl carbon is slightly positive. It's losing electron density to the oxygen there. So the OH can swoop in, attack the carbonyl carbon, kick the pi bond up, so you get this tetrahedral intermediate. tetrahedral intermediate, and the oxygen with a full negative charge is flapping in the wind, very unstable. Well, as we've seen before, that tries to snap back down. And here we have a very unusual leaving group. It's the methyl group with the 3 halogens on it. I'm going to draw the product for that, and then we'll discuss why that is a good leaving group. So once that gets ejected, we have 2 molecules. We have the OH still attached. Oops. And now we have a pi bond there. So we have a carboxylic acid. The carbon that left, this carbon here, has 3 bromines on it and a lone pair. That is normally thought of as a really unstable thing. A lone pair and a negative charge on carbon. Carbon is not a big atom, so it's not able to spread that charge out and dilute it in space. And it's not very electronegative, so it can't pull the electrons close to the nucleus and stabilize them through proximity to its protons. The reason why that is a good leaving group and why this is a relatively stable anion is because of the electronegativity of the bromines. These bromines are pulling electron density toward themselves, and that spreads this negative charge out through induction. When electron density gets spread out over multiple atoms because of electronegativity, that's called induction. And that's what stabilizes this. That's why that acts as a good leaving group. So the difference between the aldehyde and ketone chapter, on the one hand, and the carboxylic acid chapter on the other, was in the aldehyde and ketone chapter, you didn't get substitution because you didn't have a good leaving group. The magic of this haloform reaction is that it turns a carbon in a ketone into something that has a good leaving group. And once you have that good leaving group, you can do a nucleophilic acyl substitution. That's effectively what you see here. This is your sort of leaving group. The methyl group ends up turning into your leaving group, and you substitute it with the OH nucleophile. So it's a little bit of really clever magic. Now the reaction doesn't stop there. This carbon atom with the 3 bromines is still, even though it's stabilized, it's not stable. It wants to react with something, and so it attacks this acidic hydrogen. The electrons snap back there, and so you end up with not a carboxylic acid, but a carboxylate. That's a carboxylic acid that has lost its acidic hydrogen and has a full negative charge instead. So a carboxylate. That's what you end up with after that first step. And it's because it's to get the carboxylic acid back that they add hydronium. So we have the carboxylate. If you add hydronium, if you do an acid wash, then the negative oxygen there will steal this hydrogen. The electrons will snap back on the oxygen of hydronium, and you'll have your carboxylic acid. So that's the reason for that acid wash at the very end. Okay, so that replaces the methyl group that was there with an OH. Gives you your carboxylic acid. And so in this haloform reaction, you take a methyl ketone, you turn the methyl group into a good leaving group by taking the alpha hydrogens off one at a time and using that alpha carbon nucleophile to replace them with a bromine. You replace all 3 hydrogens with 3 bromines. Now that's a good leaving group, and you can do a nucleophilic acyl substitution with the OH. It comes in, you get the tetrahedral intermediate. When that snaps back down, it kicks the carbon off, and the OH is left on. One last thing is I want to talk about the name. This is called the haloform reaction, and that's because of the product that you make. The haloforms, the halo in haloform is referring to the halogens, and the form is referring to a CH, so a carbon with a hydrogen bond. So if you have a carbon with a hydrogen bond, that is this form. Just one carbon with one hydrogen, provided the other things are the same. If the other three things are the same, so either 3 chlorines, if it's 3 chlorines, those halogens are what's responsible for the halo part. So for example, if there were 3 chlorines, that would be called chloroform. That's like what in cartoon villains, put like a cloth over somebody's mouth, they fall asleep, that's chloroform. If you have the 3 bromines, then it's bromoform. And if you have 3 iodines, then it's iodoform. So all of them are forms because they all have those purple carbon to hydrogen bonds, and they're either chloroform, bromoform, or iodoform, depending on which halogen it fills in the other 3 bonds. And notice we could have done this with any halogen, right? When you look at the significant thing about this product, you don't see the bromine there. We're following the story of the carbon here. What ends up happening to the bromine is it leaves as bromoform. So this turns into bromoform after it accepts that hydrogen. If you could just as easily use chlorine, in which case you'll get chloroform, or iodine, in which case you'll get iodoform. And sometimes those are the products you really want. Maybe it's not even the carboxylic acid, but it's the haloform that you want. And so that's the reason for this reaction. So when you think haloform, you should be thinking CH and then 3 halogens. That is the good leaving group that the methyl group in the methyl ketone turns into, that allows you to do this substitution reaction with an OH. So now that we've seen what all these different pieces are doing in this mechanism, and the mechanism for this reaction, and the significance of the reaction, we'll apply those principles to synthesis exercises in the next video.